Let's decode this given equation involving logarithms. We have the logarithm of the quantity 11 minus x to the base 2 is equal to the logarithm of the quantity x plus 1 to the base 2 and then plus 3. In order for us to solve for this, we need to be reminded of the correct procedures involving properties and theorems of logarithm. To solve, let us start by trying to manipulate or isolate the logarithms on one side. Let's choose the left-hand side and we'll have this form. Let's subtract both sides by the logarithm of x plus 1 to the base 2. This would mean we will have here the logarithm of the quantity 11 minus x to the base 2. And then you subtract both sides, so we subtract here the logarithm of the quantity x plus 1 to the base 2. This would be equal to 3. Again, we just simply subtracted both sides by the logarithm of x plus 1 to the base 2. Now, why do we do this? The reason for subtracting both sides is that we now have a side where we have logarithms of the same base. We have here the base of the first logarithm is 2. The base of the second logarithm is also 2. Now, we can use another theorem or property for logarithms involving the difference of 2 of logarithms of the same base. Let us have here the logarithm of a to the base b, and if we have another logarithm, the logarithm of, let's say, c to the base b, we can just combine them into one logarithm of the same base. Take note, this will only work if we have the same base. The logarithm of the quotient of the two coefficients to the same base b. This is a property of a difference of two logarithms as long as they have the same base. With that, going back here, we can rewrite this into one logarithm because we are sure that they have the same base as 2. So we're just simply going to take their quotient, 11 of minus x over x plus 1 to the same base 2. And this is still equal to the value of 3. Then after here, we are going to use this property or theorem for logarithm when we have a logarithm of, let's say, a to the base b, and we are sure that it's equal to something, let's say, y. We can rewrite this or transform this logarithmic equation into an exponential equation, copying the base b. Y would be the exponent of that base, and this would be equal to the coefficient in your original logarithm, a. So using that here, we'll take base 2, and we have 3 as its exponent, must be equal to 11 minus x over x plus 1. So from logarithmic equation, we now have this equation here. It seems to have an exponential equation, but since this has an exact value of 8, this is now simply a rational equation, or could still be transformed into a simpler form of an equation by multiplying both sides by the denominator of this rational expression, x plus 1, so that we could cancel this here. And again, don't forget that we also multiply the other side. So copying it here, we'll have the expression by distributive property. You have 8x, and then you have plus 8 is equal to, we'll have this form here, 11 minus x. So we have now linear equation. Then we add both sides by x. So 8x plus x. And we also need to subtract both sides by 8. So 11 minus 8. Or in short, look at here. We transpose it there and here as well. You will have here a result of 9x is equal to 3. And dividing both sides by 9, your x is equal to 1/3. This is now the decoded value of the variable x in the given logarithmic equation. And by substituting that there, you will have a value, or you will satisfy the given equation. We did this by again subtracting both sides by the logarithm, by making sure that only one side contains logarithms, and we apply these properties that are applicable in order for us to reach this, following the idea of algebraic processes, including the linear equations. And that is mission accomplished.